In this lecture, we proved that if two spaces x and y are homotopically equivalent, then their fundamental groups are isomorphic. So before we prove that, we recall a fundamental fact. So say we have a path v, which is given between 2 points x and y, and both these points belong to the same space, say capital X. So then we can form a homomorphism between the fundamental groups based at space x and based at space y, and again this space capital X is where both these space points lie in. So you have this homomorphism, and this homomorphism basically via this path v is carried from one fundamental group to the other fundamental group. So you're carrying a loop u here from here to here. So this you can see in a diagram like this. So say this is point x, so this entire space is capital space X, and there is another point y, and then you have a path. So say this path is v. So then you can, this path v will induce this homomorphism, which basically takes a loop lying here. So this loop u is taken along this path to y, and the way to get the loop at y is that first to traverse in the opposite direction of the path, that is v bar. So first you traverse v bar, then you traverse along the loop u, and then you traverse along the path v back to y. So that's why we have these square green dots to tell you this is not composition, this is just traversing across the path. So the loop u here is therefore carried to the point y here. So again, first you travel in the opposite direction of this path, which is v bar, then u, and then v. So this is the theorem we want to prove. So if f x to y is homotopy equivalence, then it induces isomorphism f star between fundamental group of space x and fundamental group of space y. So another important point we want to mention here is, so if x and y are in the same path component of the space x, then you have an isomorphism here. So this is an isomorphism, and this we have talked about in previous lectures. So first implication of this theorem. So say if x and y are homotopically equivalent, so y is just a point. So then fundamental group of space x is equal to fundamental group of just a point, so which is just a trivial group. So if x is contractible, then x is equivalent to a point, homotopically equivalent to a point. So you can say its fundamental group is trivial. So space x is called simply connected if it is path connected and its fundamental group is trivial. So now we come to the proof of the theorem. So say f is a homotopy equivalence. So f is a homotopy equivalence, and therefore you have this inverse of this homotopy equivalence. So that is say map G, which will go in the opposite direction. So G goes from y to x, so opposite direction. So first you apply f, you land up in y, then you apply g, you again land up in x. So this gf is homotopy equivalent to the id on space x. So this is just from the definition of homotopy equivalence of two spaces x and y. So we have done nothing, just repeating the definition. Now we restrict these two homotopies, they are again on the same space x, to a single point x. And this will give a path, this homotopy is essentially will give us a path from x to gf of x. So again we are working in space x. So one point is x and the other point is now gf of x. So we are saying that this you get by applying this id map, this you get by applying the gf map. These are homotopy equivalent. So this homotopy is nothing but a path connecting these 2 points. So say this path is v. So this path is such that v of 0 is x and v of 1 is gf of x. So v of 0 is x and v of 1 is gf of x. So more formally you say it's a homotopy from interval times interval in the space x, such that 0t is v of t, h1 of t is again v of t, and this t lies in the second interval 0 to 1, and so v of 0 is x and v of 1 is gf of x. So this is just the way to formally write it down. So now we can construct suitable homotopies from say a loop here to gf of u here. So this loop here to corresponding loop gf of u here. So you can construct the corresponding homotopies. So homotopy goes from u to this gf of u. We are first applying, so we are constructing homotopy from here to here now. So to go from here to here, first, so this homotopy is exactly like this but in the opposite direction, because here we were trying to take the loop at point y, we are acting on this point. So now we are trying to act on this point. So instead of so now we have to start from here. So we are not starting from here, our starting point is here. So this is our starting point. So you start from here, you first apply v, then you say gfu, and then you come back v bar. So we have v, then you go to gfu, then you go to v bar. So this is exactly v bar hash of gfu. So this is just a definition here, same as this, but now we have a bar here. So the first map is double bar, so double bar was just going forward, and then back it's just single v, then u, and then v bar. So this is it. So just see that v bar has shifted, nothing else has happened. So this is the map. So this this map v hash basically is acting from x, from gfx to x, so gfu, so just like here, but now we are, instead of x, we have gf of x here. So let us first focus on this map v hash. So you can see this first part is gf, so this is gf, so it's acting on gf of x, carrying it to space x, because both x and gfx are in the same space. So this map is taking this part to this part, and that's why we need v bar, because this v is going from x to gfx, so we need v bar to go in the opposite direction. So this is this map, and both of them lie in space x, so lie in the same path component. So as we said that if they lie in the same path component, this is isomorphic, so this is an isomorphism. Now this map is an identity because this represents a homotopy from u to this v u v bar. So let us now focus on this. So first focus on this part, gfu. So for this you first apply f. So this is f. So you take loop u here, you apply f to it, you get the loop here fu. So this is our map, first map f star applying to u. Then you apply g to it. So we are working with this part, or you can say this part here. Then you apply g to it. So again you will apply g to it. So this you get map g star, which acts on loop fu, and will take it to here gfu. And then we have this v hash, which is just going to take gfu to again x. So we have this homotopy equivalence from u to v gfu v bar. So this u is finally getting mapped here as this thing. So this portion here is essentially right here, now through this thing. So do you have this homotopy here from u to this portion? So this map is an identity. So this also map is an identity. Again, this map is an identity precisely because we have been able to construct a homotopy from u, which is relative to 0 1, because it's a loop, to this v gfu v bar. So this is our identity map. So what we have to show is this f star is a identity. So again, I just mentioned before that in particular this v bar hash is an identity since f and gfx are in the same path component. So since this entire thing is an identity from here to here, it has to be the case that f star is injective. It cannot kill any elements because this map is id. So this is injective. So f star is injective. Now if you interchange f star and g star, there is no particular reason to keep g as such. We can start with g and then apply f. We can show g star is injective. So f star is injective, g star is injective. This is an iso. So it has to be the case now that these are surjective too. So, and the overall map is identity. So this is injective, this is injective, this is iso. Overall map is an identity. So it has to be the case that both f star and g star are therefore also surjective. So they are also isomorphisms, and our objective was to show that f star is an isomorphism, and that we have shown.